Hi, I'm Patrick Webb, the High-Speed DIO Product Manager at National Instruments. Today I want to talk to you about our NI PXIe 6556 high-speed digital I/O with per-pin parametric measurement unit capability. This module has 24 channels that can either dynamically generate or acquire high-speed digital signals or make DC parametric measurements. In addition, several attributes such as voltage levels, timing, and calibration can all be set on a per-channel basis. Now let me walk through a few of these tests that you might perform in an actual test system. Today I will be performing several DC parametric and functional tests on this 16-bit analog device's digital to analog converter. Here I've connected up several modular instruments in my PXI system, including a digital AT module that I just showed you, directly to the analog device's evaluation board. The small footprint of the 8 or 9 slot PXI chassis makes this setup ideal for characterization or validation lab environments. Now let me show you how I've connected these instruments specifically to the DAC. First, you can see our high-speed digital ATE module, the 6556, connected to the 16 digital lines on the DAC itself. In addition, I'm sharing a sample clock, and I'm using several digital lines to communicate over the SPI protocol to set up the DAC. Next, I'm actually powering the DAC with one of our power supplies. It's able to provide multiple voltage levels. So here we're powering with 2.5 and 3.3 volts. And then finally, the DAC is connected to one of our high-resolution, high-speed digitizers, the 5922 in this case. So the first set of tests I want to actually perform are some DC parametric tests. Typically, you want to make sure that the package is connected to the die inside the package. Here I'm doing several tests. In this top left graph, I'm actually sweeping the voltage from 0 to 7 volts on one digital pin. And I'm monitoring how much current is being pulled. This is with the device actually powered off to make sure that the protection circuitry is actually connected between the die and the package. This graph indicates that around 7 volts, the protection circuitry kicks in and sinks current. Now, we've tested the positive protection circuitry. This bottom graph illustrates testing the negative protection circuitry. And here I'm actually forcing some small amount of current, 100 nanoamps, to actually be synced to the module, the digital ATE module, from the device. So as I'm syncing that 100 nanoamps, we should see the voltage drop across the protection diode kick in. And finally, in this third graph, it illustrates the amount of leakage that the device is pulling when either a 0 or 3.3 volt signal is applied to the digital pin. Now let me just quickly hit refresh, and you can see these tests happening in real time. Another common test that you would perform on a device might be to test the threshold at which the device recognizes a digital 1 or 0. And this is called threshold testing. Here I'm going to vary the input voltage for a digital 1. So I will take a digital 1 of, say, 3.3 volts and slowly step that down until the device no longer can recognize it as a 1. And at some point, we're going to monitor the output of the device changing, and that will represent our threshold. Subsequently, I'll do that same test on the negative side. Here on the positive side, the voltage keeps changing, and finally the output changes of the device where it no longer recognizes it as a digital 1. And on the negative side, I've done the same thing, indicating a threshold for logic 1 at 1.6 volts for this device, and the device recognizing a logical 0 at about 1 volt for this device. Now, you'd also want to do several functional tests or stimulus response tests on a device like this DAC. Next, I'm going to sweep through 20 different digital waveforms and play them off my digital AT module and feed them into the input of the DAC, and then measure the response of the DAC with the high-speed, high-resolution digitizer. So as I sweep through those 20 different digital waveforms, you see on the bottom right-hand side here the spectrum being captured by the digitizer. Let me run this one more time. You can see the waveforms being captured very quickly. And then in LabVIEWer and C, I can perform a variety of analysis to measure the actual performance of the device. While the digital AT module can be used for validation tests, it's also ideal for production tests. If I use a single 18-slot PXI system, I can scale my test system to test up to 6 DACs simultaneously. In this test system, each DAC is connected to its own digital AT module, and I still have room for several high-resolution digitizers and power supplies. Not only do we have parallel hardware in this test system, But with the help of NI LabVIEW and NI TestStan, we can run the software in parallel as well. Here in this TestStan operator interface, you can see that I'm running a set of production tests on all 6 DACs simultaneously, allowing us to achieve a production test system with speeds of up to 12 DACs per second. In summary, this digital AT module is ideal for testing a variety of components, from validation labs to production floors. I encourage you to go and investigate the rest of the features of the NI PXIe 6556 digital AT module. I'm sure you'll find it essential for your next system.